Consultant with the IES Cognition and Student Learning Prize-winning paper for this conference.
Hi everyone, thanks for coming out to our session. As some of you might have known, I've changed the title to something more fitting. I would also like to point out that this award is also going out to our co-authors who deserve it as much as I do. So Vincent Vallejo is also in the audience, so Vincent, please stand up a little bit. See you? Yes. Come on. Allow me to give you a meta-level kind of overview of what we're trying to do in our project, and then I'll start to dive into the details of it. So what we're trying to do with the project is support learners in the acquisition of complex problem-solving skills. And in our project, that's going to be geometry skills. And how we're going to do this, we're combining two successful research traditions, cognitive tutors of CMU and the Word example tradition. So here's two main questions that we're trying to address. And you might recognize the first one because it's derived from the original title. Are work examples and cognitive tutors redundant or synergistic forms of support for learning? And the second question, can examples make learning with cognitive tutor more robust and efficient? So, short overview of what I'm going to talk about. Cognitive tutors, you've seen a small screenshot of the algebra tutor and Julie's talk. When I'm talking about cognitive tutors in this talk, I mean the geometry tutor. It's similar, but it definitely has several differences, and you'll see those in quite a bunch of screenshots. Give a short recap of the word examples literature. I'll talk about our project in which we combine the word examples and embedded them in the cognitive tutors. I'll breeze before studies and some results, and finally give some conclusions, discussion, and tell you what we're doing right now. So cognitive tutors, long-standing tradition in improving students' learning, describing cognitive theory, ACT-R for instance. There's step-by-step guidance. We use cognitive models, student thinking, and there's many full-year class year evaluations showing that it actually improves students' learning. So, cognitive tutors. There's 5 key elements, in my opinion, that are tailored towards the individual student. And here's the interface of the geometry tutor that we're using. Feedback. As you can see, when a student performs an incorrect action, it's marked as incorrect. There's also implicit positive feedback, in which the tutor accepts. It doesn't mark anything, but it simply accepts the correct action. Second key element, stepwise hints. Pretty much for every step that the student has to do with the tutor, he or she can ask for specific hints for that step to perform it. Third key element, the glossary. It shows you an overview of all the relevant geometry rules that are in the tutor. Let's just look them up, look up the definition. There's even a small example underneath it. The fourth key element is student self-explanation. So students do not only have to find the value, but also actually have to think about the value and the concept that lies behind it and self-explain what concept is really important to find that value. The fifth key element is not so apparent to the student, but more to us as researchers, which is the mastery learning, and it basically keeps track of the student's progress throughout the curriculum, and it decides whether or not to get students remedial problems if they have not fully mastered the problem skills yet. By default, this mastery learning is turned on in the classroom because we have agreed with the school that they're turned on, but in the lab environment we turn them off because that will allow us to find or obtain the full effects of our experimental interventions. And again, it's turned on in the classroom because we want to avoid any possible negative effects that might have on the students' learning. So what examples? The second long-standing tradition in improving students' learning. Pretty much every combination of examples and problems seems to be consistently better than problems only. Initial help, in this case, the word examples, eventually become redundant as students gain more knowledge throughout their learning process. This phenomenon is also known as the expertise reversal effect. And this is also relevant for our studies that I'll be talking about in a bit. You depthly fading examples based on the individual student's progress in the training. It's better than doing that in a one-size-fits-all fixed manner where everybody gets the exact same fading procedure and everybody gets faded steps at the exact same point in time to drive the training. And both of these fading procedures are better than problem solving only. Also, the research on word examples has mostly been paper-based, and comparison to the counter tutor, there's no corrective feedback, no hints are given, there's no glossary, the students can use master learning is totally non-existent. So basically, research on word examples so far has been in an untutored environment. And in our project, excuse me, we're combining those two. So we're embedding that word example research in a tutored problem-solving environment. And by that, we're making it pretty hard on ourselves because the control condition is much harder than the one that they usually have in the word example literature. So here's a question that ties into one of the main questions again. Will an example which cognitive tutor still show a beneficial effect above and beyond the built-in assistance of the standard cognitive tutor? So in order to test this, we did 2 lab studies which we compared problem-solving conditions versus a word example condition. Obviously, we expect the example condition to outperform the problem-solving condition. Examples were gradually fitted in a fixed manner, so everybody gets the exact same grading procedure, and everybody gets fade step at the exact same point in time to arrive at training. And there were 7 problems in this training curriculum for them. So again, here's a reminder of what the cognitive tutor looks like, and the experimental condition, which is pretty much the same as the control condition, in that students can ask for hints, get corrective feedback, look up the glossary, etc. But as you can see, the value steps actually worked out. And we don't just give the value, but we actually also give the calculation steps. And it's important to know that students still have to self-explain that value step. So it's not, they still have to think about these steps. So they still have to figure out, okay, what geometry concept was applied in order to find that value. So results from these 2 studies. Basically what we found was that the example condition completed the training sequence much faster than the problem-solving condition and still was able to obtain the exact same transfer performance. So the example condition was a lot more efficient. And one result that we also found in our second lab study was that on the conceptual knowledge items that the word examples outperformed the problem-solving condition. So this is all fine and dandy, word examples in a tutored problem-solving environment lead to more effective training, but will they also work in the actual in vivo setting, which is the actual classroom? And can we further improve their effectiveness if we adaptively fade to the individual student's progress? So in order to test these 2 questions, we did a lab study and an in vivo study with 3 conditions. The first 2 conditions are the exact same as the first study, the third 2 lab studies, problem solving, which is standard cognitive tutor, fixed fading, where one size fit all fading happened, and adaptive fading, which was based on the quality of the self-explanations. So let me go back very fast. So these self-explanations, that's what it was based on, when and how to fade for these students in this condition. That was assessed by the tutor, and obviously students who self-explain better receive fewer examples than students who are poorly in self-explanation. We're going to pre, post-test, and delay post-test to test effects. And it's important to note that the mastery learning was turned off in the last study, but was turned on in the in vivo study. So that means that students in our in vivo study will have received remedial problems, whereas the students in the lab study have not. Okay, drum rolls. So results for the lab study. The adaptive fading condition outperformed the 2 other conditions on both the post-test and the delay post-test. So will this effect also appear in the in vivo study? So here's what we found there. Even in our in vivo environment, we found some benefit, and the benefit was between the adaptive fading condition outperforming the problem-solving condition on the delayed post-test. That's not a 100% replication, but here's another reminder. We turned mastery learning on in the in vivo study, so that might have washed out possible effects of our interventions. Some conclusions from the 2 lab and in vivo studies. Starting with word examples is consistently better than tutored problem solving, which is in agreement with another PCC member, Bruce McLaren, who also has a poster. I think it's tomorrow night. Here's the page number on the CD proceedings if you want to look it up. And he also found that examples are more efficient than problem solving. Second conclusion, adaptive fading of examples is better than tutored problem solving only. Thus, and again tying back into one of our main questions, word examples and cognitive tutors are not redundant, but actually synergistic forms of support for learning. Now, let me to give you a slide on the discussion board, which is an open issue, and we do not have the answers to it, but somebody told me that John Anderson knows everything. So if you have any questions about this slide, ask John. He's sitting in the audience, so. So this is a question that we're pondering about, and in our opinion, it's a very important and interesting one. So why is turning a problem step into an example step not the same as presenting an example step? And with that, we mean presenting example steps basically work that step, but students who are working in the problem-solving condition can turn that problem step into an example step by using the hints. So basically, every hint sequence for every single step has a bottom-up hint which gives them the answer. Possible explanations are causal flows, for instance. Students who start working on the problem, do a problem-solving task, they will have to invest a lot more mental effort in order to deal with that task and try to solve it, compared to someone who gets a word and example. Also, it might be that people who start on a problem-solving task will attend to several different relevant features of the problem at hand than people who receive a word and example. Also, motivation. You can definitely see that some teenage students will be more inclined to find the answers that they've done with their problems and start focusing on more important issues in their life. But other students might focus more on actually understanding the material at hand and try to figure out this math. Also, another motivation-related point is that some students will get frustrated after working on a pure problem and getting incorrect. Student tells them it's incorrect every single time, and they're starting to get really frustrated and want to get the hell out of their classroom in the problem-solving condition. But if you get a worked out example, then the frustration level might be a bit lower because you get all these worked out steps and you can think about how they did it, and then later on you can finally get a first attempt yourself. So what are we doing right now? So we're very, very happy with the results so far, and it's awesome to get an award for this, but we're scientists and we're always looking for bigger and better things. So further improvement will be to have a more principal adaptive fading procedure. And in order to get that procedure, we recently completed 2 preparatory studies which we tested the existence of an inverted U-shaped curve. And with that, basically on the y-axis, it indicates learning, and on the x-axis, the number of vortex steps. And that ties in with the expertise reversal effect, because that tells you that initially vortex steps would help, but later on, if you continue to give students who already have gained that knowledge, if you continue to give them vortex steps, that might actually harm their learning. So that's hopefully what we're going to find. We haven't done an analysis, but as it says, the analysis will start shortly, and you'll have to wait until next year's winning paper. All right, thank you. John.
I have a version of your discussion question. Is what you did different than just volunteering from the bottom up? So students can reach the bottom up by saying help, help, help. You can just give it to them without any request. What's the difference between what you did and doing that? Is that what you did, or is there something different?
Basically, the hints are somewhat similar to the word steps that we give, but they're not 100% similar. Basically, the initial premises that we have is that students who are starting working in a new domain like geometry, the circle section that we're doing in this project, need some additional help in the beginning. So that's why we give the word steps. But there's also this other research that you might be familiar with, Ryan Baker's gaming the system, in which students can click to the hints and then finally get to the hint last final bottom up hint, and then copy that and then continue to work until they fill out everything and not really learn anything, but they get the task done. I'm still wondering about this issue, why it's not the same. I don't have the answer, like I said.
The actual text they read is different, is that right? So
there's more wording.
Either you just compose better text, in this case, than the text that's available through the hint process.
It's possible. Basically, the word steps are more aimed towards the formula, the calculations that they have to do, while the hints are more textual hints. And the bottom-out hint does basically give you the bottom-out value, but it needs more text compared to the calculations.
Are all the steps presented at once with the worked out example?
No.
They're not.
It's basically every single step, like, let me go back to screenshot. So for instance, What we did was, this was only a single step problem, but for every subsequent step, it's not worked out yet until the student reaches that step. So basically, it will give you a blank spot in the table, which is in the upper right corner. It will be a blank spot, but once the student self-explains, let's see, what is it? This measure of R, BFD? Yeah. Once he fills that one in, then the next step will be filled in on the blank spot for the next arc or angle, whatever it is. Further questions? Okay, thank you for your attention.